Jai Hind all. This is Neeti Pahuja, Assistant Professor, Department of Computer Science and Engineering, Akgec Engineering College. Today, I am going to discuss a very important topic of computer organization and architecture, which is cache memory. I'll be preparing a series of lectures. In this series, I'll be completing all the aspects. I'll be covering all the aspects of the cache memory in detail. So this lecture is the start of the series, and following lectures will cover the complete concepts. In this lecture, I'll discuss about the introductory part of cache memory. To start with, let's have the first slide that says it is basically the principle behind cache memory. So our cache memory, as we know, it is a small size memory in which we keep the data which is frequently accessed. So as a layman, we know this much about cache memory, that it holds the frequently accessed data by the CPU. So the basic principle, first we'll study that on which the cache memory works. It is the principle of locality of reference. So locality of reference, as its name suggests, that locality, so locality means the neighborhood. Locality is basically the neighborhood of anything. It may be the neighborhood of any person or neighborhood of anywhere. So locality in this context means the locality of reference of a particular variable or a data item which is referred by the CPU. So we know the basic architecture of the system, that we have a CPU and it processes all the informations, all the instructions inside the CPU. So the CPU needs to contact the main memory of the system. Since all the programs in execution are kept in the main memory, so the CPU accesses the main memory to get the items on which it needs to operate. So the basic principle behind locality of reference or the cache memory is that the CPU, when accesses the main memory, it takes some time to get the data from there. For example, if the CPU main memory access time is, let's say, 20 nanoseconds, it takes 20 nanoseconds to get an item from there, and it has to take 100 instructions or maybe 100 data items. So the total time taken by CPU to access this main memory will be 20 into 1000, that is 2000 nanoseconds. This much time will be wasted only in accessing the content from there. Then we will start with the processing. So our objective is that we need to minimize this access time. We need to reduce this access time. For that, what we have done, we have implemented a new kind of memory in the computer system, which is faster, which is having the lesser time of execution, the lesser time of accessing. That memory is known as cache memory, and it is based on the principle of locality of reference. Now, what this locality of reference says, it says the references to memory at any given time interval tend to be confined. It is important term, confined within a localized area. That means we assume that, let's say, CPU accesses this portion of the main memory. Our main memory is divided into multiple blocks. We know this about the main memory, that it is divided into blocks, and on each of the block we are having some amount of data kept on it. So when the CPU makes a reference to this particular block, for example, it wanted to access this particular item, so the scientist and the scientists conducted various experiments, and on basis of those experiments and observations, they concluded that if the CPU accesses a particular item in a memory block, there are high chances that the items which are around this particular accessed items are then likely to be accessed. That is, the next access is confined within a localized area. So the confined access is restricted to this much, that if this particular item has been accessed now, the next item to be accessed will be either this or this. There are high chances of that. And this particular area is then called the locality of this particular reference. Reference means the data item or the instruction to which the CPU made an access, and locality means the neighboring amount of this particular variable is called the locality. So the references at any given time are confined within this much local area, and the area contains a set of information about the membership that changes gradually as the time goes by. Now, on the basis of time and space, we define this locality twice in two ways. First is the temporal locality and other is the spatial locality. Let's discuss the spatial locality first. For example, if the CPU accessed the data at location number 99, there are high chances, high probability that it will access the data at location 100 next, 101 next, and so till the time this block continues. This is called spatial locality of reference. That means the data item where it was last accessed, the next reference that the CPU will make to the neighboring items, and this complete neighborhood is defined by a block. We call this neighborhood as a block in the main memory. Fine. Another kind of memory reference is temporal locality of reference. That is, if I access 99 at this particular time, there are high chances that I'll refer 99 again in some time. In some time I'll access again this particular element. So there we have two types of locality: temporal locality of reference and spatial locality of reference. Example of spatial locality of reference is data items in array. Array is a set of similar kind of data structures. So the CPU referred if this particular data item, then it will for sure access the next and next and next by the time there are elements in the array. This is called spatial locality of reference. And the example of temporal locality of reference is the reuse of information in loops. For example, I access I right now, then if I am accessing it in a loop, inside a loop, so it will be accessed quite frequently the next time. Fine. Now our objective is to make a faster memory. So this, on the basis of this locality of principle, locality of reference principle, what we do is we identify the CPU access the main memory. Fine. And it accessed a particular data item, for example here. So CPU made a reference for this one. Now the system has defined a block as the locality of this data item. Fine. For the frequent access, we assume if the CPU has accessed this data, now it will definitely access the data neighbor to it. So the neighborhood is defined in a block, and that block itself will be kept in a faster memory. So we'll be having one more unit of memory, which is called the cache memory. Now what we will do is the CPU will refer to this data item, the CPU will maintain a locality of reference, and on the basis of this principle, this block will be kept in a faster memory. Faster means faster because cache has a different underlying architecture on which it is based. It is a flip-flop based memory that does not need any kind of refreshing. So it is fast in accessing CPU as compared to the main memory. The cache is near to the CPU. So location also matters, and what matters is the underlying architecture of the cache memory. That is why we call this as a faster memory. So what we have done is we just used this data and kept it in the cache memory. So the next time when the CPU is going to use this data, it will not search in the main memory, it will search in the cache memory first. So now we can say, earlier example that I have told, that if the cache access time was 20 nanosecond and we had to process 100 such instructions, so the total time taken was 2000 nanoseconds, and our objective was to reduce this total access time. Now suppose the cache access time is 5 nanoseconds. What we have done now is we took this data block and put it in the cache. Now the same 100 items when accessed from the cache memory will take only 500 nanoseconds to be accessed. Fine. So we can say if we move this data to the cache memory, the total cache access, the total memory access time is reduced by a much number. Fine. So cache is a fast, small capacity memory. This is how we define the cache memory. It is a small capacity fast memory that should hold those information which are most likely to be accessed. Now why we are calling it most likely to be accessed? because we have selected these values on the basis of locality of reference principle that I have explained just now. Fine. So this is the diagram depicting the cache memory, that we have the CPU which processes the instructions. We have a main memory in which we hold the current information or current data to be processed. Out of this memory, when the CPU makes references to the main memory, it finds out a block where the frequent data are accessed, where the data are accessed frequently. So we use this block and put this block in the cache memory. Now the memory access time of this cache memory is quite less as compared to the memory access time of the main memory, and it is also near to the CPU. So this will reduce the total accessing time from the memory location. Fine. Next are the issues in performance, how the performance of this cache memory works. So the all memory accesses are directed first to the cache memory. Using that same diagram again, when the CPU wants any reference now, instead of searching in the main memory, it will first search in the cache memory. Fine. So first it is directed to find in the cache. If the word in the CPU is in the cache, if the CPU accesses the cache and it found the word there, then access cache to provide it to the CPU. Then it fetches the word from there only. And if it was not in the cache, then what happens? Then that block is searched in the main memory, and it is the responsibility of CPU to get that block from the main memory to the cache memory. Fine. So if the word is not in the cache, bring a block including that word to replace a block now in the cache. Explaining this more, let's suppose this was the CPU. Here I have put the cache memory, and now we have the main memory. So earlier our operation was that the CPU, whenever it wanted some data, what it used to do? It used to access the main memory for that. Now we have put cache in place. So the CPU will search in the cache. If the data item is matched in cache, then it's good. It's a hit. And if that particular data item was not in cache, then the CPU will search for the main memory. It will access the data from there. Also, on the basis of locality of that accessed data item, it will place this block in the cache, so that the next time the CPU references the cache, it will get the data item there. Now, how we can know if the word that is required is there? How the system will get to know? The system is not able to get anything on its own. We need to program it. We need to feed the information to it. So how the system will get to know that if I am referring to data item 100, the data item that I got in this cache block, it is actually the same or the different one. So we need to make a mechanism how the system can get to know that it is the correct data. Another issue is, if a new block is to be replaced, then one of the old blocks has to go from there. Now, which one should we choose to replace? For example, we have 4 blocks in the cache memory. Fine. There are 4 blocks in the cache memory, and all of these 4 blocks are filled now. Now, my CPU wanted some data. It referred to the cache memory, searched the cache memory, and the data was not found in any of the blocks. Then what will happen? It will go to the main memory. It will access the data item from there. Also, it will get the data from main memory into one of these cache blocks. Now, in which cache block it will place the data? Since it is already occupied by all the blocks, which cache block would be replaced to get this new data? This is the issue. Now, the problem to these two issues will be resolved in the next slides. Fine. To tell the performance of a cache memory system, we have one major concept which is known as the hit ratio. Now, what is hit ratio? Hit ratio is, let's see the definition first. It is the percentage of memory accesses satisfied by the cache memory system. That means the CPU wanted some data, it checked into the cache memory and found the data over there, then this situation is called a hit. Now, CPU wanted some data, it searched the cache memory and the wanted information is not found in the cache, then this situation is called as miss. Fine. The hit may be defined as this, hit ratio has a formula on the basis of this concept that CPU wanted some data, it found it in the cache memory, and this is the hit. So hit ratio may be defined as the number of hits out of the total memory references. Total memory references. For example, the CPU referred the cache memory 100 times. Fine. It referred to the cache memory. It searched the cache memory 100 times for some data items. And out of those 100 times, it found the data in the cache 40 times. So the hit ratio will be 40%. Is this clear? It referred the cache memory 100 times. Out of those 100 times, 40 times it found the data in the cache memory. So the hit ratio is 40%. Now, if this number has to be defined, the ratio, then we can say that the hit ratio lies in the range. The range will be the minimum and the maximum. We need to define both values. So the minimum value can be that CPU referenced the cache memory and it never found any data. All the data were not present in the cache. In that case, it will be number of hits will be 0 and total number may be anything. So minimum value of this hit ratio can be 0. That all of the time it made references, there was no data found in the cache. Maximum can be that it referenced the cache memory 100 times, n times, and out of those n times, all times the data was present in the cache. Then our hit ratio value will be 1. So hit ratio lies in the range 0 to 1. Using this convention, what we can find is, if the data is found in the cache, then it is called a hit. If it is not found in the cache, this is called a miss situation. If we know the value of hit, then the value of miss is equals to, miss is actually 1 minus hit. Fine. That is, if there was a hit ratio of 40%, then the value of miss ratio will be 40% time the data is found on the cache, but 60% of the time it is not actually found in the cache. Then the miss ratio is 60%. Fine. On the basis of this hit ratio and miss ratio, we can calculate the average access time. Fine. For that, we have assumed two things, that the cache memory access time is TC, main memory access time is TM, and we can now calculate the average access time. Average access time means the CPU referred the memory for some data calculations, for some references. Out of those times, there were times when the data it was found in the cache, and there will be time when it used the data, it wanted some data and it is not found in the cache. So when there was a hit, only the cache memory will be accessed. So the time will be, if it is a hit, then only the cache memory access time is taken. If the hit was not there, there was a miss. If it was a miss is defined by 1 minus h, then our main memory will be accessed. So the total time in this case will be hit to TCM time will be taken to get the data, and if it is a miss, then TM time will be taken to get the data from the main memory. Now it should be actually divided by 2, but since we are already using this value as reference, we are using this as ratio, so we are not dividing the context by 2. Here I have used an example as well. If cache memory access time is 0.4 second and main memory access time is 1.2 second, obviously the cache memory access time will be less since it is a faster memory, and main memory access time would be more, and the hit ratio is 0.85. that is 85% of the time the CPU, when referred the cache, it found the data over there. Fine. So the average time can be 0.4 plus 1 minus 0.5 into 1.2, which is the main memory access time. Fine. Now this accessing can also be of two types. We can also divide the access in two ways. We can define it. It may be a hierarchical access or it may be a simultaneous access. Let me define these two terms for you. Look at this. There I have a CPU, then also we have a cache memory, and finally we have a main memory. Now, when the CPU wants some data, will it access the cache first, or it will access the main memory first, or it will access both? The answer to this question lies in this. It can access the cache memory and the main memory in two ways. First, let's discuss the simultaneous. Simultaneous means the CPU wanted some data and it simultaneously access the cache memory and main memory. For example, let the time begin at t is equals to 0. The cache memory access time is 20 nanoseconds and the main memory access time is, let's say, 50 nanoseconds. So at t is equals to 0, it started to search in the cache. Also, on the same time, it started to search in the main memory. If there was a hit, then average access time will be, if there is a hit, then average access time will be cache memory access time only. Fine. If we found the data in cache, there is no need to further find it in the main memory. Otherwise, if there is a miss, then we'll continue with main memory. We had already started searching the main memory. If it is found there, we'll stop. If it is not found, then we'll keep on searching in the main memory and get the data from there. In simultaneous, the average access formula will be this. How about in hierarchy? Hierarchy means first we will search the cache memory. If the data is found over there, it's good. If the data is not found over there, then we'll start searching for the main memory. That is, we started at t is equals to 20. First, we will go for cache memory for 20 nanoseconds. Fine. If it is a hit, then in 20 nanoseconds, we can search for the data. If the data was not found there, that is, it was a miss. In the case of miss, we have already spent 30 nanoseconds. Now we will search for another 50 nanoseconds and then we will get the data. So in the case of hierarchical access, hit ratio, if it is a hit, then cache access time is only taken. After this cache has been searched and we have not got any data, then we will start with searching the main memory. So in case of miss, first we will search the cache memory, then we will start searching the main memory. So in this case, average access time will be this. There are two cases. Fine. A hierarchy, that is step by step, we'll first search the cache and then search the main memory, and simultaneous means both are accessed together. Right? I hope this will be clear. Now, cache memory is a special high-speed memory. The cache is smaller and faster memory that stores the copies of data from frequently used main memory locations. That I have already told this thing that the data which is accessed right now in the main memory, its locality will be searched and that searched locality will be placed back into the cache memory. There are variations, different independent, there are various different independent caches in a CPU which stores instructions and data. There are hierarchy of cache memories, L1 cache, L2 cache. We will discuss these later. The most important use of cache memory is that it is used to reduce the average time to access the data. That I have told you how we can calculate this average time. And the next things will be how we access the cache, how we write the cache, and what are the ways to search in the cache. So in the next lecture, I will be discussing the next concepts. Thank you so much.